Not that complicated. With Ava and Jacob.
Welcome back to another video with Jacob, and today we will be discussing collisions. Below we have a simple example that states two students are playing billiards incorrectly. A 150-gram ball and a 200-gram ball are both hit at a speed of 3.6 kilometers an hour towards each other. After the elastic collision, the balls bounce off each other. Determine their final speeds. In the question, it states an elastic collision, which means automatically that momentum and kinetic energy are conserved. When momentum is conserved, its initial momentum and its final momentum is going to be equal, and also the initial energy of the system and the final energy of the system will also be the same. As always, it's always important to draw out the question so we can better visualize what is going on. It's also important to label your masses correctly and also your velocity, especially if your initial velocities are different. Next, we notice that in the question, we are dealing with grams and kilometers an hour. In physics, it's always best to deal with the basic units of kilograms and meters per second. We know how to convert from grams to kilograms. We just divide by 1,000. To convert 3.6 kilometers an hour to some value in meters per second, we can convert step by step each conversion. So we know that in 1 kilometer there's 1,000 meters. We know that in 1 hour there's 60 minutes, and we know that in 1 minute there's 60 seconds. So by using these fraction style conversions, we can cancel the units and pick out the units that we'd like to use. And in this case, it's meters per second. This equals 1 meter per second. There's also a trick. When converting kilometers per hour to meters per second, we can just divide by 3.6. It makes our lives a little bit easier. You can also, from going meters to seconds to kilometers an hour, you can multiply by 3.6. To be better organized in the problem, we can separate the location of the masses, mass 1 and mass 2, and deal with them separately until we need to combine them. Mass 1, we have 150 grams, which converts to 0.1 kilograms, and then mass 2 is 200 grams, which converts to 0.2 kilograms. Then we have our initial velocity for our mass 1, which is 1 meter per second, and we have our initial velocity of mass 2, which is also 1 meter per second. Now, this value is negative because the direction of the ball for mass 2 is moving in the opposite direction to mass 1. And velocity is a vector, so it's necessary to include your magnitude and your direction. Now, the goal of this problem is to find the final velocity of the mass 1 and the final velocity of mass 2. Since momentum is conserved, we know that the momentum prior to the collision and the momentum after the collision need to be equal. And here is the formula below. Then we plug in our known values. We have two unknowns we want to solve for, right? The final velocity of mass 1 and the final velocity of mass 2. We can now use two equations to solve for two unknowns, and our two equations are the conservation of momentum equation and the conservation of kinetic energy equation. And kinetic energy is conserved because there's no frictional forces acting on it, and the kinetic energy of the system prior to the collision and after the collision remain the same since the collision is elastic. That means that the initial energy is equal to the final energy. We can recall that the formula for kinetic energy is 1/2 mv squared, and we can now create a formula for the conservation of kinetic energy. We can now multiply the equation by 2 to cancel the 1/2's. We can now plug in our values, and there we have our second equation. Now that we have two equations and two unknowns, we can isolate for one of the variables in one equation and plug it back into our second equation. We do this to get one equation in terms of one variable and one unknown. Now looking at our conservation of kinetic energy equation, it's harder to isolate in this equation. Therefore, we'll go back up to our conservation of momentum equation and isolate for V 2f, which is the final velocity for the second mass. And when we go back to our conservation of kinetic energy, whenever we see the final velocity of mass 2, we'll plug in our first equation back into here so we can get this in terms of only the final velocity of mass 1. It is easier if we distribute the fraction into the actual numbers, and if we do so, we'll get negative 0.25 minus 0.75 VIF, which is the final velocity for mass 1. And that's all equal to the final velocity of mass 2. Since this is squared, we can rewrite this equation so it'd be easier to distribute the values and multiply each one. After doing basic multiplication and addition, as well as collecting like terms, although this is a tedious process, it's important to keep your values to 3 significant digits, as it'll improve the precision of your final answer. We notice here that in order to solve for this quadratic equation, we need to use the quadratic formula. And we do that by reorganizing this equation and putting 0.35 on the right side of the equation. When we do 0.0125 minus 0.35, we get negative 0.3375, and we keep the same terms from the equation above for the other values. And we can recall quadratic formula to be negative b plus minus root b squared minus 4ac over 2a, and that all equals to the final velocity of mass 1, since that's the unknown in this equation. And in every case for the quadratic formula, we get 2 solutions. Now we have to decipher which one will be correct. Our first solution is 1 meter per second, and our second solution is negative 1.29 meters per second. 1 meter per second for the final velocity of mass 1 is the same as its initial velocity. Now, that means that the speed of the ball did not change, and it also means that direction didn't change, which goes against what the question is saying, that they actually collided, and this would mean that we can discard it right away. Now we know that our solution for the final velocity for mass 1 is negative 1.29 meters per second. Now we can sub that value back into our equation for the final velocity of mass 2, and we get that the final velocity of mass 2 is 0.72 meters per second. Therefore, the final speed for the first mass of 150 grams is 1.29 meters per second in the opposite direction. And the final speed for the second mass of 200 grams is 0.72 meters per second. And there you go. I hope this solves some of your questions about collisions, and enjoy the rest of your studies.
Thank you for watching Not That Complicated. Don't forget to like and subscribe.